All right, so picking up with what we were talking about there not too long ago here. In the first part of this lecture, we were talking about the idea of common ion. And as we just saw through sort of the calculation and example, again, the presence of that common ion is going to suppress that solid from breaking apart. So um, it is going to end up on this side, our common ion. Going to force Le Chatelier's principle to the left and again decrease our solubility. So as we saw, I think in the example there was silver bromide. In water, it was like 0.0002 grams per 100,000 milliliters of water. With the common ion present, I think it dropped to like 0.000002 grams. So much, much smaller solubility. So I think the next thing we got up is an example. So why don't you give it a go here? The KSP of silver chromate is 9 times 10 to the minus 12. What would be the solubility of this compound in a solution that has 0.1 molar potassium chromate? You could do molar solubility is fine on this one. So you could do molar solubility. All right, so take a few moments. Okay, let's take a look. So again, we know a couple things here. We do have a KSP given to us. So this guy is going to be the one that sets up our equilibrium. So we definitely will have our silver chromate here, breaking apart in this case into a couple of silver ions and a chromate there. And we do have the KSP for this, and we can write our KSP expression, which would be the silver concentration. Once again, we do need to square it because of the 2, times the chromate. And that's going to equal 9 times 10 to the minus 12 here. We also have this not in water, but we do have it in, if I go find it, there it is, in a solution that has potassium chromate in it. And potassium chromate is K2CrO4. And that is going to be a strong electrolyte, which will break apart into a couple of potassiums and a chromate here. And again, hopefully you could recognize that it is the chromate in this case. That is going to be our common ion, right? So that is going to be our common ion that is here. And we'll go that way, common ion. So we do know how much of the chromate we have, and it is 0.1 molar. Once again, it's a 1-to-1 relationship between the chromate and the whole thing, which means the molarity basically stays the same. You multiply it by 1. A reminder that if for some reason you needed the potassium, you would have to multiply the concentration by 2 because it's a 1-to-2 relationship, and that would give you 0.2 molar for the potassium. Obviously not needed in this problem, but again, that's how molarity works. So we're going to do an ice table here, and that common ion is going to be inserted here in the initial as it's in the solution to begin with. So we got 0.1 molar again being supplied by the potassium chromate in this case. Change going to be plus 2s, once again, because of the coefficient, and plus s. That means at equilibrium, we got a 2s, a 0.1 plus s. Any questions on the table here? Now that we have it, we're going to go into our expression. So that is going to give us, looks like 2s. Remember, we still need to square it as well, times 0.1 plus s equals 9 times 10 to the minus 12. Just like we did on sort of the example that we finished up on, we definitely have a small value of k. So we can assume here s is equal to 0. Once again, it is going to be that S right there that we're going to get rid of. That will basically get us 4S squared times 0.1 is equal to 9 times 10 to the minus 12. However you want to do it. If you want to take 4 times 0.1 gets you 0.4. S squared equals 9 times 10 to the minus 12. You could also divide each of those separately as well. We're going to divide that to the other side. I can find my button I'm looking for. There it is. And that's going to give us here an S squared is equal to 2.25 times 10 to the minus 11. Again, we're going to square root there both sides. And that's going to give us here a molar solubility of, again, a lot of zeros there. Looks like 4.7 times 10 to the minus 6 moles per liter, or the molar solubility here of our silver chromate with a 2 there in this particular case. We obviously could check it. So again, if you took that, divided it by 0.1, times it by 100, you're good. You're nowhere near 0.1%. So like I said, in most cases, you'll probably be pretty good on the check here, as the KSP is pretty small in this case. Obviously, if we wanted grams per liter, we could use our molar mass of silver chromate to get that. Any questions on that? Also a reminder, though, in this particular case, if we were looking for the silver concentration in the solution, we would have to take that S value and times it by 2, right? And if we were looking for the chromate's concentration in this solution, we would have to pop it back into here to get that as well. So remember, although the S, and a lot of times we're just kind of looking for the solubility of the entire thing, you may have a question to ask, kind of like, what are the concentration of the ions in that solution? So you would just put it back into the ice table like you would do with your X value. Any questions on that there? So one of the things that can affect solubility is the presence of a common ion. And as we see in these couple of examples, what it does again is keeps that guy together, decreases the solubility of it. The next thing that we're going to talk about that can affect the solubility of something is actually pH and solubility. So pH plays a really important role in terms of solubility of things. So as we just saw, again, that presence of that common ion will decrease the solubility. Insoluble bases will dissolve in acidic solutions, and insoluble acids will dissolve in basic solutions. So the pH plays a really big role in terms of solubility. So for example, here, if we look at magnesium hydroxide, which is an insoluble base, we can use the KSP value and kind of go through our calculation and figure out a couple of important things to help us understand maybe what's going on with the pH. So I'm gonna actually just pop the KSP up here. I think 1.2 times 10 to the minus 11. Pop that back. So if we go through this here and do our ice table, this is going to be 0 and 0. Change here would be plus S. Once again, we do have a 2 there, so that's going to be plus 2S. And at equilibrium, we would have S and 2S. Again, if we put this into our KSP expression that was up there a second ago, which is the magnesium times the hydroxide, and again, we do need to square it because of the coefficient, that's going to get us basically S times 2S squared is equal to 1.2 times 10 to the minus 11. Remembering to square the number as well gets you something like 4S cubed is equal to 1.2 times 10 to the minus 11. Going to divide the 4 to the other side and then take the cube root of it afterwards. And we'll go 1.2 to the minus 11 divided by 4 and take our cube root. will get us an S that is equal to 1.4 times 10 to the minus 4. And again, that is molar in this case. First off, any questions on that there? Now, I think we've talked about it, but just in case in terms of your calculator, right? If you don't have a button like that and you need to do something like the cubed root, fourth root, you could do a caret, parentheses, 1 divided by 3, right? And that will basically do the cubed root. 1 divided by 2 would be the square root. 1 divided by 4 would be the fourth root, and so forth. So in case you don't have a button like that on your calculator, you could kind of do the caret and just take 1 divided by whatever root you're trying to do, and then that will do it for you. That is the molar solubility here of magnesium hydroxide in moles per liter. And in terms of the pH, we actually can put this S back into here and get us a hydroxide concentration. So if I put it into here for my hydroxide, it does equal 2 times S, which would give me 2 times 1.4 to the minus 4. I'm just going to use the whole number in my calculator there. And that's going to get me about a 2.88 times 10 to the minus 4 molar. That is useful because I could calculate my pOH from that. And my pOH in this case would then be negative log of 2.88 times 10 to the minus 4. And it'd give me like a 3.54 pOH. And my pH finally here would be 14 minus that. And it looks like a 1046 pH here. So in addition to obviously figuring out the molar solubility here of magnesium hydroxide, which again, I could also use the molar mass to figure out grams per liter of it, I know that this particular solution is hanging out at a pH of 10.46. That also makes sense, right? Because it is a base, right? So we would hopefully expect kind of a basic pH in most cases. So how does that number sort of help us understand what could happen in terms of the solubility of magnesium hydroxide? So if you have this solution, for example, and you decide to decrease the pH to less than 10.46, what will happen? How can I decrease the pH? What should I add? Acid or base? I should add an acid, right? So to drop the pH below 10.46, you're going to add an acid. And essentially, when you add an acid, you're really just adding, in most cases, H plus, right? That's basically what makes it an acid. So you're adding some more H plus to this solution. That's going to have an effect on the solution because when you add H plus, it is going to do what? It's going to react with. It is clearly not there, right? So we're not adding more of it, right? So it's not in that equilibrium, but it should react with our friend hydroxide, right? And H plus and hydroxide will make water. Yep. So we'll make some water here. The result of that is ultimately in terms of hydroxide, it's going to decrease the concentration of hydroxide, right? And that would be essentially removing hydroxide, right? Which means Le Chatelier's principle will tell us the equilibrium should shift which way. In this case, it should shift towards the hydroxide, right? To fill that hole. So we would cause an equilibrium to shift to the right. The result of that is in these equilibriums, on the right-hand side is aqueous ions, which means it is going to start to dissolve more, right? So you'll actually start to see the solid go away in this case because the equilibrium is going to shift to the right and you'll actually have more solubility. So by adding acid here, we're actually going to increase the solubility of this particular solution. Any questions on that? Do I need to get it to an acidic pH to see that happen? The answer is no. You just got to drop it below that magic number of 10.46. Yeah. So as soon as you drop it below that pH of where it was at 10.46, even though the pH of that solution is still basic, that's enough to cause that equilibrium to shift to the right, and you will start to see, obviously, the solid go away. The further down you go, you might actually see all the solid disappear, right, and kind of go to the right. But again, that is what it means above, where it says an insoluble base like this is soluble in acidic solutions. So even if you have something, again, based on solubility rules, that should be a solid, if you change, obviously, in this particular example here, the pH lower than where that solution started, you'll actually start to see it become more and more soluble as you lower the pH. Any questions on that? So obviously here, what would happen if we kind of did the opposite here and we went and decided, all right, we lowered the pH, let's bring the pH higher. So if we increase the pH, can you see that color or no? Yeah. We'll go different. We'll go blue. So if we increase the pH above 10.46, and if we increase pH above 10.46, obviously the way that we could do that is we need to add some more base to that solution, right? Base should bring the pH up. Essentially, when you add base, you are adding OH minus. So in the case of the base situation here, if you decide to bring the pH above 10.46, you're going to increase the concentration of hydroxide. In this particular case, we actually have hydroxide in the equilibrium. So this time, though, we are raising the hydroxide. And again, Le Chatelier's principle tells us that in this case, we're increasing the hydroxide. That should cause the equilibrium to shift away from the side we're increasing it. And you should see a shift to the left in this particular case. And that definitely is going to head towards the solid side of that equilibrium. And that is definitely going to decrease the solubility. So especially in acidic salts or basic salts, because acidic salts may have H plus or basic salts will have OH minus, you could actually get like a baseline pH of that solution. And again, if you kind of go above or below, depending on what it is, you can either increase the solubility or decrease the solubility, depending on what you want to kind of achieve there. So pH plays a really big role. There's experiments we don't do here anymore, but part of those kind of experiments, which are known as qualitative analysis, we'll see just a little picture of it shortly. A lot of the times you are doing that type of situation where you're kind of just changing the pH, and the idea is to kind of keep certain ions floating around in solution and make other ions less soluble and going to come out of solution and kind of selectively precipitate out things. So playing with pH is a big factor in terms of solubility. Any questions on that there? All right. The sort of third thing that's a major impact on solubility is really concentration and the concentration of the ions that are floating around in that solution. So the concentration of ions in solution plays a really big effect as to whether or not you will see a precipitate form, even if it's supposed to. So again, based on solubility rules, you may come across something that says these two things are insoluble. If you do not have the right concentration of those ions in solution, you may actually not see the precipitate form, even though solubility rules tell you it should. This is where we use Q versus K as P. And a reminder that, as we talked about earlier, Q is calculated the same as the KSP. So Q is calculated the same as KSP. And again, as we've been talking about, obviously solid on the left, aqueous ions on the right. So if Q is greater than the KSP, basically goes opposite the way it's pointing, it will go towards the reactant side, and you would expect a precipitate to form in that situation, kind of a supersaturated solution. If you have Q that's less than the KSP, opposite the way it's pointing, we'll go to our aqueous side, and you would not expect a solid to form. You have sort of an unsaturated solution at that point. And you would need to do a couple other things to kind of see that form. Now, this happens a lot, for example, when you do experiments. And you may sometimes not see a precipitate form when you're doing an experiment because you were a little heavy-handed with like reagents, right? So every time we add a reagent that's not a solid but a solution, we're essentially doing what to that solution? We're essentially diluting it, right? Because you're adding more volume, more water. So if you're like really heavy-handed with the reagents and you add too much of a reagent, you may lower the concentration of your ions in that solution to a point where you will not see the precipitate form, even though it should perform based on solubility rules. So that's a really big effect on solubility, is the concentration. And it can affect certain tests that you do if you're looking for a precipitate to form at the end of a sort of experiment to sort of confirm something was there. And if you added too much reagents along the way, really diluted down your solution, you oftentimes may not see the actual test work correctly for you at the end. That's why, for example, in those qualitative analysis sort of experiments, they have a lot of procedures because they add a lot of reagents. They have a lot of procedures where they heat the solution to evaporate off also that excess water, make them more concentrated so that tests and these type of things will work so that the concentration of your ions are much higher. All right, so let's take a look at one here. If a 2 milliliters of a 0.2 molar sodium hydroxide solution is added to 1 liter of a 0.1 molar calcium chloride solution, would we expect a precipitate to form? So really the first thing you want to think about is there anything there that could potentially make a precipitate? So we're basically throwing into our pool here sodium hydroxide, which is basically a source of sodium ions and hydroxide ions. We're also tossing into the swimming pool there some calcium chloride, and that's going to give us some calcium ions and chloride ions. So again, the only option of solids that could form is when these guys swap partners. So that would be these guys coming together, and that would be basically these guys coming together. So again, hopefully you know sodium is pretty much soluble in everything. So that definitely would not make a solid. So really in this case, it is perhaps the combination of calcium hydroxide that has the possibility, based off of solubility rules, to actually form a solid. Now, with that being said, if you weren't sure of your solubility rules, you probably want to refer to a KSP table and see if you find any of those combinations up there, and you will find calcium hydroxide up there, and that should tell you that should be the solid. So as I mentioned earlier, if you're not 100% on the solubility rules, you could use your KSP table. It probably wouldn't be up there if it was not a solid or would form a solid, has the potential to form a solid. So in this case here, if we did look up the KSP for our only option of a solid, which is our calcium hydroxide, it is 8 times 10 to the minus 6. So why don't you pick it up from there? Why don't you calculate Q and see if we would get a solid? All right, so let's take a look. So obviously here we do want to compare Q to KSP. Q again is going to be calculated the same as the KSP. And again, that is based off of how this guy would break apart. And again, it would break apart into a calcium ion and 2 hydroxide ions. So just like the KSP is above based off of that, Q in this case would be the concentration of calcium times the concentration of hydroxide. And again, we are still squaring it because of the coefficient. What we need here, though, is the concentration of each of those ions in the beaker that we put together. So this is a dilution type situation here. So our hydroxide is going to come from our sodium hydroxide. That's going to be our source of the hydroxide ions here. And we need to do maybe a little M1 V1 equals M2 V2 action here. I'm going to get the volumes into the same units, and you could either use liters or milliliters. I'm going to use milliliters. So 1 liter is 1,000 milliliters, right? And then we're going to add basically 2 milliliters of our other solution. So we're going to end up with 1,002 milliliters, or obviously if you went to liters, 1.002 liters if you did it in liters. So that is going to be our final volume, right, when we put it together. So for the hydroxide here, we used 2 milliliters of it. And its concentration was 0.2 molar divided by the entire volume, which is our V2. Milliliters will cancel, and that's going to leave us molarity here. And for the hydroxide, it looks like we have here, I'll just call it 3.99 times 10 to the minus 4 molar. We're going to do the same thing there for our calcium. And once again, the calcium chloride is the only source of our calcium in this case. So our calcium, we use there 1,000 milliliters of it, which is 1 liter. And its molarity is 0.1 molar divided by our total volume of 1,002. And that's going to give us our correct concentration of calcium in this case. And if I punched in better, that would be good as well, probably. Divided by 1,002. And that's going to give us about a 9.98 times 10 to the minus 2 molar. First off, any questions on that there? So now that we have the actual concentrations of these ions that are floating around in that beaker, we could put it into our Q expression and see what's going to happen. So if we take our calcium, which was the 9.98 number, times it by our hydroxide, which is 3.99 times 10 to the minus 4. Don't forget to square it, right? That's going to get us here. Take that and a little squared action times 9.98 to the minus 2. It's going to get us a Q of 1.6 times 10 to the minus 8. Any questions on that there? Okay. So now we have the Q, and obviously we have the KSP from the table. In this case, Q versus the KSP. Q is actually less than the KSP. Again, minus 8 versus minus 6, right? So because Q is less than the KSP, goes opposite the way it points towards the product side. And again, in the product side of all these are aqueous ions, which means no precipitate will form in this case. So again, another example that although based on solubility rules, it says, hey, if you toss in there some calcium, some hydroxide, you probably will get a solid. In this case, we do not have the right concentration of the ions floating around in the solution to actually produce that precipitate. Any questions on that there? So again, those are 3 really important things in terms of solubility. Concentration, pH, and common ion can have a very big effect on the solubility of things. Now, we're going to talk about here another aspect of KSP and really a useful aspect of KSP. And that is the idea of what is known as selective precipitation. And selective precipitation is pretty much what it sounds like. You got a swimming pool of ions floating around. And you want to add something to this. And by the way, that is where we find ions in solution floating around. You want to add a reagent to it to precipitate out only one of the ions. So for example, let's just say we want to add something that will precipitate out the A. So we'll add some C minus to it. And C minus, when it added, will find the A and precipitate those guys out as AC sort of solid here. Just kind of precipitate these guys out. That would leave our B guys still floating around in the solution. And you can use KSP to help you kind of figure out, okay, what concentration do I need to use for that precipitating reagent? Like C would be our precipitating reagent here, is the thing we're adding to precipitate out some ion. And you could use solubility rules, obviously, to figure out what you should add to cause a precipitate to form. But you could also use the KSP to figure out, how much you need to add to actually see it. As we just saw in the last example, although you may find something based on solubility rules that should make it precipitate, if you don't add it in the right concentration, you may not see the precipitate actually form. So you could use KSP to really dial in how much of that precipitating reagent you should do. So let's just kind of go through an example of this and sort of illustrate how we could use that. So let's say we had a solution like we do here, and basically in that solution, we have bromide ions floating around and we have chloride ions basically floating around. And in this particular case, we want to add silver to it. So we want to add some silver ion to it. The silver here would be our precipitating reagent. As based on solubility rules, we know bromide and chloride are soluble in everything except for silver, lead, and mercury. So silver is going to cause a solid to form. Now, we want to make sure that we're able to add silver correctly to allow this to happen. Now, the concentration of our ions here, both of them are 0.2 molar. So both of these guys floating around in here is 0.02 molar in terms of their concentration. Now, why would you perhaps want to selectively precipitate these out and not just go, let me just dump the bucket of silver in there and get some solid basically to come out? The reason is sort of what the picture displays. Silver chloride and silver bromide solid are both basically white type solids. So if you are not careful when you add your silver, you're just going to get a bunch of white solid, and you can't like go through it and go, I think this one is like the silver chloride, I think like this crystal is the silver bromide. You're not going to be able obviously to tell the difference. So here what we want to do is keep one in solution, take one out, so that we're confident that when we start to actually see a solid form, we're confident that that solid is this thing. And that's what the idea of selective precipitation is all about. That's also the idea of what those experiments I was talking about a second ago, which are qualitative analysis experiments, are all about. You selectively precipitate out ions from solution, and you leave other ones floating around. Be happy that you don't do that crap anymore, stuff anymore, those type of experiments here anymore, because they usually use not the greatest of reagents and stuff like that. Years ago, this type of class, that would be all you did for the entire lab portion was these type of experiments as precipitate out. So most schools have gotten rid of that. A lot of schools still do it, but most schools got rid of it almost completely. And they did here as well. We used to just do like one of those type of experiments, but they got rid of it. All right, so back to the problem here. We do know our two potential solids, silver bromide and silver chloride. We can look up, obviously, our KSP values in here. And we see the KSP for our silver bromide is 7.7 times 10 to the minus 13. And our silver chloride is 1.6 times 10 to the minus 10. So if I write my KSP expression here for my silver bromide, that is the silver concentration times the bromide concentration, and that's going to equal 7.7 times 10 to the minus 13. Now, I am interested in how much silver I should add, or what concentration of silver I should add to get the bromide to come out of solution. So remember, our goal here is just to get the bromide to precipitate out first and leave the chloride ions still floating around. So the goal here is to take this guy and kind of bring it out as a solid, leave this guy happily floating around in the solution. So if I solve for silver here, concentration, and rearrange our KSP expression, we get 7.7 times 10 to the minus 13 divided by the concentration of bromide. And I already know the concentration of bromide. It was given to me in the problem is 0.02. So if I pop those guys in, we will end up with a silver concentration of, and we'll call it 3.9 times 10 to the minus 11 molar. So 3.9 times 10 to the minus 11 molar. This number right here represents the minimum concentration of silver that is needed to start to see a precipitate form. So that is the minimum concentration that's needed to start to see specifically here silver bromide form. Questions on that? Now we could do pretty much the identical type of calculation for our other possible solid, which is silver chloride. So again, if we write our KSP for silver chloride, it is the silver concentration times the chloride concentration, and that equals our 1.6 times 10 to the minus 10. Again, we do know the concentration of the chloride that's in the solution. It is 0.02 molar. That means we can rearrange here and solve for silver, which would be 1.6 times 10 to the minus 10 divided by our bromide concentration. Putting in our numbers here, 1.6 times 10 to the minus 10 divided by 0.02 molar is going to give us a silver concentration of 8 times 10 to the minus 9 molar here. This number represents the minimum concentration of silver needed to precipitate out silver chloride. First off, any questions on that? So what that means is which one is larger in terms of the concentration of silver needed? Yeah, AgCl is larger, right? So that means that if I want to start to precipitate out my silver bromide, I need to toss in there at least a concentration of 3.9 times 10 to the minus 11 molar. Needs to be my silver concentration, right? Now, if I do that, I should start to see precipitate form. And I can feel very confident that the precipitate that is forming is silver bromide. And that is because in order to get silver chloride to precipitate out, you need a silver concentration greater than 8.0 times 10 to the minus 9. So you need a silver concentration that is greater than that number. So if I keep my silver concentration between those two numbers, I will start to see a solid form as I hit 3.9 times 10 to the minus 11. As long as I keep my silver concentration less than 8 times 10 to the minus 9, I would see solid form, and I can know that that solid should be silver bromide. And if you were doing this, you would add the silver at 3.9 times 10 to the minus 11, start to see that precipitate. You could continuously kind of slowly increase your concentration of silver, again, keeping it below 8 times 10 to the minus 9. And at some point, you will probably stop seeing solid form. You maybe have precipitated out all of the bromide as silver bromide. Then what you could do is start to increase your silver concentration greater than 8 times 10 to the minus 9. You should, at that point, once again start to see solid form. And that solid should be silver chloride. And that, again, is a selective way that you can precipitate out all the chloride ions from the bromide ions by controlling the concentration of the precipitating reagent, which in this case is the silver ion. And again, if we just added silver at a concentration greater than 8 times 10 to the minus 9, what will happen? If at the beginning we just dumped in there a concentration greater than 8 times 10 to the minus 9, what should happen at that point? Yeah, everybody's just going to come out as solution, right? Everybody's getting out of the pool together, right? Everybody's coming out. You'll have no idea to know which one's which, right? And again, that is a value of what KSP can give you is if you're doing experiments where you need to kind of just leave one guy in solution, take one guy out at a time, you could use those KSP values to figure out the actual concentration that is necessary to do that. Any questions on that there? Yeah.
Concentration to the precipitates break apart to create the silver bromide, or is it two separate matters?
So if I understand your question, are you asking how you would kind of separate them out? Yeah. So what you would do is you would obviously do some type of calculation like this and sort of figure out the concentration that you need. So what you would do is you would, for example, here, pop it back here. So you would have your bromide ions floating around and your chloride ions floating around. And you go, okay, I'm just going to keep my silver concentration below chloride, but enough to actually see bromide. So when you add it, you're going to form all this solid, and we'll just call it red at this point, but it is a white solid. What you would actually do is you would pop that into something like a centrifuge, spin it around really quick. And basically what will happen is all that solid will find a corner of your tube and your solution, which still has the chloride going that. You could pour off the solution, right? And now in a separate sort of beaker, you have just chloride in there, right? Ideally. And now you have your silver bromide stuck in the centrifuge sieve, if you will, or that container that you can do whatever you want with it. And at this point, once you add that silver, you'll now just see more solid form. You can do the same thing to isolate the solid and stuff like that. And that's how you would do a sort of a selective precipitation. You kind of, the idea of it, and that is really the idea of those qualitative analysis experiments is you selectively precipitate out either one ion or a group of ions as a solid. You centrifuge it, you pour the liquid off, which has the other ions floating around in it, and then you take that solid and do whatever you would like with it. For example, if you wanted then to free up, for example, you centrifuged out like your silver chloride and you want to actually free it up to get the silver away from the chloride, you could pop some ammonia in there. And that actually will rip apart the silver and the chloride from each other. And it will actually put the silver into a complex ion, which we'll talk about shortly here. And it will actually be aqueous and it'll be floating around in the solution. So, and that's the idea of those type of experiments as well, is you kind of get everybody out as a precipitate, and then to that precipitate, you kind of send some ions into solution and selectively take them out with specific tests to test for what's present. Other questions? Yeah. So that is selective precipitation. The last thing on this is, why did the question ask, or why is the question written, that we wanted to precipitate out silver bromide first, could we have precipitated out silver chloride first? The answer is no, based on the calculation that we did, right? Could we have figured that out without doing a calculation in this case? Which one should come out of solution first? The answer is yes, because in this case, they both make how many ions? They both make 2 ions, right? And because they both make 2 ions there, right? And obviously 2 ions there. That is what we were talking about earlier today, that you could actually use the KSP value to figure out which one should be more soluble or less soluble. And when we compare the KSP values, which you can do in this case because they make the same number of ions, we see that the silver chloride is a larger KSP value, which means it should be more soluble and will stay in solution longer than this guy that has a lower KSP value. So in this particular case, if you were just given a beaker of like, here's some chloride, here's some bromide, which one do you think should come out first? This is a case where you could look at the KSP and go, I think if we choose the right precipitating reagent, the silver bromide definitely should come out first because it has a smaller KSP. It should be less soluble than the silver chloride in this case. Question on that there. Okay. So as I was mentioned before, and I kind of touched upon it, we don't really do that in these experiments anymore, but these are what are known as qualitative analysis experiments. And qualitative analysis experiments are broken up by groups, group 1, group 2, group 3, group 4, and sometimes 4 and 5 are together. And they're not, by the way, groups based off the periodic table. They are groups based on solubility rules. And right here is our basically chloride, bromide, iodide solubility rule. They are soluble in everything except for chloride, bromide, and iodide, silver, mercury 1, and lead 2. So in these experiments, you have a precipitating reagent, and that is why we use, for example, hydrochloric acid as a source of chloride to precipitate out those guys. Now, these precipitating reagents for group 2 and group 3 are actually the same. It's hydrogen sulfide gas, which is also why you should be happy you don't play with it. If you ever smelled sulfur, it's a terrible experiment as well. One school I was at, they do it in fume hoods because of the sulfur. And as soon as everybody dropped like the sulfur, the fume hoods went out and died. So we had the entire room like, oh, get rid of that quickly, get rid of it, and call the day over because not a pleasant smell. But the idea here, though, between group 2 and group 3, just to illustrate another point of what we've been talking about, is they actually use the same exact precipitating reagent, really some sulfide. And the difference, though, is one is very, very acidic. And that's the idea we were talking about before, pH. So if you had a beaker of like group 2 ions and group 3 ions floating around, you can keep group 3 ions in the solution by making the solution super acidic. And that is not the right pH condition for those group 3 ions to precipitate out. Even though they're both using the exact same thing to cause the precipitate, like the sulfur, because the pH is super low for group 2, like 0.5 pH, really, really acidic, that will allow group 2 to actually precipitate out under those acidic conditions. Then what you could do is actually swap it the other way and make it really, really basic. And now you're going to have the right environment for those group 3 ions to come out. So those are the things we were talking about earlier, that pH could play a really important role in terms of whether or not something will precipitate or out. And you can use it to your advantage in a situation like this if you want to get only a certain set of ions out, even if you're using the same precipitating reagent. By playing with that pH, you could really selectively precipitate out. And it's what makes students kind of crazy when they read instructions when they do those experiments, because in the same 2 sentences it says make your solution acidic, next sentence make it basic, next sentence make it acidic again. So there's a lot of playing with pH when you do those type of experiments. And the point of that is what we were talking about there, that allows the right environment for whether or not a precipitate will form or not. That's what you look like when you do that experiment, perhaps. And our favorite thing on those experiments is some things are soluble in everything. So you cannot precipitate out certain things like sodium, potassium, stuff like that. So when you get down to group 4 or 5, a lot of times you're just relying upon flame tests to identify what elements may be present. If you ever done a flame test before, that's a crappy way to identify things. But, you know, people are always going like, hey, do you see purple or not see purple for potassium? And it's a very tough thing at the end there. All right, any questions on KSP solubility? One more topic here to talk about, and we'll wrap up here chapter 15. So the next thing we're going to talk about, now that we sort of talked about KSP, and KSP, as we saw, our equilibrium constant values, obviously for our insoluble solids, they are typically very small values. Here with complex ion, we're actually going to go sort of to the other end of the extreme, and we're going to talk about KF, and KF is the equilibrium constant for complex ions. Now, a complex ion is basically a metal ion in the middle, and attached to it is one or more molecules. These molecules are what are referred to as being ligands, and ligands are Lewis bases. So if you remember in chapter 14, we talked about Lewis acids and Lewis bases, and remember that they deal with electrons. And a Lewis base is something that will actually donate a pair of electrons. So a Lewis base donates the pair of electrons. A Lewis acid accepts a pair of electrons. And that is why the metal that's in the middle, that's an ion and positively charged, is a good Lewis acid, because if you're positively charged, you have lost electrons, you're electron deficient, and you're willing to accept electrons. So they make really good Lewis acids, and ligands are good Lewis bases. Here's an example of that. We have cobalt, which has a +2 charge, and usually a lot of times in complex ions, the metal is usually a transition metal-ish. And here, this is going to be our ligand, our Lewis base, which is the chloride. Chloride is negatively charged, and things that are negatively charged have extra electrons, which means they're more apt to donate those electrons. So that makes them really good. Comes together and makes our cobalt with a -2 charge. We could write an equilibrium expression for this, which is our products over our reactants. And it is our complex ion over our cobalt. And once again, we are still doing our normal coefficients, obviously, as the squares here. This is the formation constant, is the equilibrium constant for a complex ion. And as the KF value increases, the stability of the complex ion also increases. So what that means is, again, if we have a large value for K, we would expect mainly products, and products over here is our complex ion in this case. So basically in this case, we have a cobalt in the middle. It is attached to 4 chlorides, and overall it has a -2 charge, and that is because the cobalt's +2, and each of the chlorides are -1, right? So -4 and +2 gives you a -2 overall charge that's happening in this case. Now, when we talk about ligands that come on, they actually do come on one at a time. So although what we are looking at here in this particular equation is sort of the end result of what happens, the ligands come on kind of like how hydrogens get lost one at a time. They come on one at a time. So what would happen in this case is the cobalt would pick up 1 chloride and make COCl, and this would be plus. And there would actually be a K value associated with just that first sort of chloride that comes on. Then this guy that picks up or one of the chlorides already will pick up another chloride and make COCl2. And there could be an equilibrium expression constant for that as well. Then this guy that's now picked up 2 chlorides will pick up lucky number 3 here, chloride. And we'll get COCl3 -1 at this point. Also an equilibrium value for that. And lastly here, COCl3 minus will pick up one more chloride, giving us COCl4 2 minus in this case. And that would be an equilibrium. So ligands go on in a stepwise fashion. So they're added in a stepwise fashion here. So what we are seeing in this equation here is actually the overall reaction, because if we add these together, this cancels, this cancels, this cancels, and we are left with CO2 plus 1, 2, 3, and 4 chlorides. Makes our complex ion here that has all 4 chlorides on it. So again, it does happen in a stepwise fashion. By the way, if I had only the steps given to me and the K values for each of the steps, how would I get the KF? KF would be equal to what with those K values? I do multiply and not add, right? So here we would want to multiply. So we would multiply all those guys together. Yeah. Again, not adding. So sometimes in these problems, they will give you kind of the overall sort of equation that's happening wherein all the ligands are attached. Sometimes you may be given like the stepwise sort of formation of it as well. So by the way, each of these steps are equilibrium steps, which means if you got some type of equilibrium concentrations, you're good to go with the individual steps, and you could use the individual steps to solve for things as well. Any questions on that there? Now, as I mentioned before, ligands are things that can donate a pair of electrons. So things that are really good ligands are polar molecules, like our friend water here. Water is polar. It's got some non-bonding electrons there on a polar sort of atom as well. NH3, same deal. Got some electrons there and it's polar. Chloride, like we just saw, has a negative charge. So again, it's got extra electrons to give. There is something that we'll talk more about in a later chapter, but just for now, it is sometimes referred to as the coordination number when you're dealing with complex ions. And the coordination number is actually the number of atoms that are directly attached to the metal in a complex ion. So if you take the one that we just looked at there with the cobalt and the chlorides, attached directly to that cobalt are 4 atoms, and the coordination number would be 4. If we look at something like cobalt and we use water as our guy here, water would attach to the oxygen, as that is where the electrons are, and it's more negative as well. 1, 2, 3, 4, squeeze it in here, 5 and 6. So in this particular case, we got 1 oxygen atom, 2 oxygen atoms, 3, 4, 5, and 6 that are directly attached to that metal, and that is why it has a coordination number of 6. Now, one of the things that people sometimes think, which is incorrect, is, well, can I just look at this number and go, it's 6, and this number is 4? And the answer is no, not in all cases. You can in these cases because there are different types of ligands. And for example, all these ligands that are listed here, these are what are referred to as being monodentate. Mono meaning 1. So each of these molecules will only attach to the metal in one spot through one atom. And that is why it does match. But there are some ligands, as we'll talk more about in a later chapter as well, which are known as being bidentate, for example. A common one is oxalate. Oxalate is bidentate. And if you draw oxalate, it looks something like this, I believe. 99% sure. And this is oxalate. And when you have a metal ion, it has the ability to attach through both of those single bonded oxygens, as they are the ones actually carrying the negative charge. And that means you get like a 2-for-1 special on this one. You get 2 bonds for 1 molecule. So if you had another oxalate on the other side, it also could attach like that. So if you looked at the formula, you might see something like, I'll just put a metal and C2O4 and whatever the charge is. And you might just see a 2 down there. And in this case, the coordination number is not 2. The coordination number for this guy would actually be 4. And it is 4 because you get 2 for 1 in each molecule. So there's 2, 3, and 4 molecules that are attached. So it does depend on the ligand as to how many places it could attach, as to what the proper coordination number is. And again, if you have a bidentate, you get 2 for 1. There are some that attach in 3 places per ligand. There's some that attach in like 6 places or 8 places per ligand. They attach in a lot of places. So very common coordination numbers, though, are 2, 4, and 6. Those are very common coordination numbers. And usually things, for example, with like a +1 charge, we'll do like a coordination number of 2. Something with like a +2 charge, we'll do like 4, and +3, sometimes we'll do 6. And that's because the more electron deficient the atom is, the higher the positive charge, the more apt it's available to have more things attached to it and have a greater coordination number, a greater number of atoms that bond to it. Any questions on that there? All right, so let's take a look at this problem here, and we're going to go through this one here together just to explain some of the different things that we do in these type of calculations that we maybe don't do in others. And we're going to take 0.2 moles of copper 2 sulfate and mix it with a liter of 1.2 molar ammonia. And we want to know what is the concentration of copper in the solution, free copper, at equilibrium. Now, just for this example, and we don't do it for all examples, just to kind of keep everybody's numbers not too crazy-ish, we're going to assume that all volumes stay at 1 liter. And again, that's not always the case. Obviously, you will have to take into account the volume as well. But just for this example, we're going to assume that. So the first thing we have is our KF value here, and we can write our KF expression, which is like normal. So it's going to be our products, which is our complex ion, divided by our reactants, which is our copper 2 and our NH3. And once again, we do need to take it to the 4th power because of the coefficient. We are going to do an ice table here, and we're going to do an ice table with molarity. And typically speaking, it is probably the best course of action to do this ice table with molarity. And you want really the molarity of everybody once they're mixed together. So a lot of times you will have to do like an M1V1 equals M2V2 sort of situation. But you do want to kind of the concentration of everybody in here together when they're mixed. So since I'm going to assume that this guy is 1 liter as well, I'm just going to turn that guy into 0.2 molar. And this guy's already in there, and everybody's staying at 1 liter. So that will be its concentration as well. Again, you will sometimes have to take into account, obviously, the volume usually. So we're going to do our ice table here. And initially, we have 0.2 molar of our copper 2 ion. And that is going to be coming from our copper 2 sulfate. So that's going to be the source of the copper 2 ions that are floating around. The sulfate here is just like a spectator ion. It's not doing much. It's just kind of floating around in the solution. Ammonia obviously is going to be our source of ammonia, which is 1.2 molar. And this is going to be 0. Now, normally when we do a table like this with molarity, we typically use X's, correct? So typically speaking, if we went through and did this like a normal ice table, we would come through and go minus X, minus 4X, and plus X is typically what we would do. Now, one of the things that we do a little bit different when we do these type of problems is based off of the KF value here, is that a large or small value? It is a large value. That's a fairly large value. And what that means is we should definitely expect when this reaches equilibrium to basically be all products. Yeah. So it is so large that the first assumption we make is we first assume that all the concentration of the metal is used up and goes to form the complex ion. Now, since the copper in this case is the metal that's in the middle of the complex ion, it is kind of like our limiting reagent. It's once that is gone, we can't make any more complex ions. So because the K value is so large, we're going to assume for the sake of this calculation that it is kind of like a one-way direction. It's all going towards the product side. And this is going to definitely be our limiting reagent because you just can't make a complex ion if you don't have any more of that metal left. So when we assume that, we kind of change our calculation a little bit here in the change part of it. And instead of using X's, we actually know what our change is going to be. It is going to always be the metal ion is going to be the change. So instead of using X's, I'll go underneath it. We'll just go minus 0.2. This would be minus 4 times 0.2, right? Again, we still got to take the coefficient into account. And this would be plus 0.2. Yeah. Any questions on that? So we kind of actually use a number usually in this calculation, not X's. So it's kind of one of the few places where we kind of use molarity and not use X's and just kind of use numbers. We usually do that with moles, which technically would work with moles, but you got to remember about the volume at the end. So it's just better to do it in molarity up front. So it all works out okay. So here at the end, we're going to end up with 0 for our copper 2 ion, which was our assumption. We're going to end up with 1.2 minus 0.4 times, not 0.4, 4 times 0.2. There we go. We're going to end up with here 0.4 molar, and we're going to end up with 0.2 molar. So at the end of this ice table, for example, if we want to know what is the concentration of the complex ion, we actually have it. We have 0.2 molar would be the concentration of complex ion. If we want to know how much ammonia we would have left, we actually know that as well, right? It would be 0.4 molar. Now, the question was about how much copper, free copper, is floating around in this solution at equilibrium. And clearly here we zeroed it out, which means this would not be much of a problem if the answer was always 0, right? You just can write 0 and move on. But this is where the second part of the assumption comes into play. The second part is, even though that is a really large K value, it is still an equilibrium reaction. Which means even though almost 100% of it is heading to the product side, there will be a smidge of it going back the other way. So there will be a small amount of those products still breaking apart into the ions that we see on the reactant side. So a small amount of it's going to come back the other way. What that means is the copper concentration or the metal concentration, the metal ion concentration, should be a really small number. So that is the second part of the assumption, which is even though we're assuming originally it's all going to the product side, all the metal ions going to get used up, it is still an equilibrium reaction, which means it should come back a little bit. And what we should end up with is a very, very small number for the free, in this case, copper ions that are floating around in the solution. So how can we get to that number? Well, we actually can use our KF expression here. And what we're going to do is, even though we zeroed this guy out, we are going to go, okay, some of it's going to come back. So let's find out how much of it's going to come back. And we're just going to call it X at this point to try to figure out how much of it did kind of come back. So using our KF expression, we would have that the concentration of our complex ion was 0.2 molar from our table, divided by the concentration of the copper that is free. That's what we're trying to find. And our concentration of our NH3, which is 0.4, that we do need to take to the fourth, equals our KF value, which was 5 times 10 to the 13. So if we rearrange this, these two guys basically just switch places, multiply the copper to the other side, divide by the KF, and that will get you 0.2 divided by 5 times 10 to the 13 times our 0.4 to the fourth would equal our free copper 2 concentration. So we're going to end up with, in this case, 0.2 divided by 5 to the 13 divided by 0.4 to the fourth. And that's going to get us a copper concentration of 1.6 times 10 to the minus 13 molar. Is that concentration a big number or a small number? It's like a super small number. Basically, there's nothing there, right? And that validates our first assumption that pretty much all of that copper is going to be tied up in that complex ion. But if you want to call it and go out about 12 decimal places to the left or to the right, you'll have a little bit of free copper ions floating around. So the formation, as you can see here, of a complex ion is super favored because if there is a ligand present and a metal, they're going to want to form that complex ion. And as you can see, pretty much all that metal gets tied up in the complex ion. There's not a lot of free metal left over. And that's why they're sometimes referred to ligands as chelating agents, things that grab metals, right? So they're very good at grabbing onto metals and tying them up. This is also a good point that if you did this calculation, you ended up with a really large number for your copper, you screwed up, yes? Because it should definitely be a very small number here, super small number, or really small number that is freely floating. Because again, the reason we have these really large K values is it is favored to make the complex ion, which means it is favored to go to the right and make products, and means that we should have a small amount of free ions floating around. Any questions on that there? All right, now we understand the assumptions. Let's take a look at this one. We want to calculate the concentration of silver, the AgS2O3 minus, the AgS2O3 3 minus, in a solution that's prepared by mixing 150 milliliters of 1 times 10 to minus 3 silver nitrate with 200 milliliters of Na2S2O3 5 molar. They actually gave you a stepwise formation down here. So why don't you give it a go, work through it, see what you come up with. You could combo those things together. Clearly here we are not keeping the volumes constant, so you do have to take that into consideration. Maybe some M1 V1 equals M2 V2 action. All right, give it a go, see what you come up with. Okay, let's take a look, see how we're doing here. So we are given a stepwise sort of formation here. We can add these guys together if we like, and we can get sort of an overall reaction that's sort of happening here. And we could kind of get rid of those guys, and that would give us that we basically have silver plus a couple of these guys here. going to make our S2O3 2 minus. If we wanted to, we could get our KF for this by multiplying these guys together. And that would be 7.4 to the 8, it looks like. To the 8 times 3.9 to the 4. Oops, come back here. Maybe. There we go. I'll hide it to the 4th. And that's going to give us, it equals 2.9 times 10 to the 13 as our KF here for the overall reaction. Now, we could use this overall sort of equation reaction. Since we're really looking for like everybody's concentration, we could use this to help us get some of the concentrations we're looking for. We do need to take into account the volumes, and we're mixing these things together. So we're going to be looking for the concentrations that everybody mixed together. Obviously, here our silver nitrate is our source of silver, and our S2O3 is going to come from our other one here, as this is a source of this guy here. So those are our sources of those two things. So we're going to do a little M1 V1 equals M2 V2 here. So for our silver concentration, we are using 150 milliliters of it. And we have 1 times 10 to the minus 3 as concentration, divided by our total volume, which in this case is 150 plus 200. So that's 350 milliliters is our total volume once we mix everybody together. Milliliters cancel, leaves us molarity. And that means for our silver here, we got something like, I'll call it 4.29 times 10. 1, 2, 3 minus 4 molar. We could do the same thing for our other sort of reactant there, our S2O3 2 minus. We're going to use 200 milliliters of it. It is 5 molar. And again, our total volume here, once we throw everybody together, 350 milliliters. Going to give us 200 times 5 divided by 350. Looks like a 2.86 molar here. Any questions so far? All right, so if I take the sort of overall reaction here, which I think is again going to be our silver plus our couple of these guys, making our complex ion there, Ag S2O3 2 3 minus. And we take our initial as we just calculated there for our silver, 4.29 to the minus 4. And 2.86 there for our second, and a 0. Once again here, as we saw with our KF value that we calculated, it is a large value for KF, so we can make our assumption like we talked about previously. So we're going to assume that all of the silver is going to get tied up here. So we're going to assume all the silver gets used up. So once again here, our change is going to be minus 4.29 times 10 to the minus 4, minus 2 times 4.29 times 10 to the minus 4. Again, that'll be like our 2x that we normally would put there. So we got to take that coefficient into account, plus 4.29 times 10 to the minus 4. Any questions on that line there? Bringing us now to equilibrium here. We're going to end up with 0 of that. We got 2.86 minus 2 times 4.29 to the minus 4. Going to get us basically 2.86 still. And that's going to get us here, obviously, 4.29 times 10 to the minus 4 molar. All right. At the end of this table, we actually hit 2 concentrations. We now know the concentration of our complex ion. So we have this guy's concentration, check. We also have the S2O3 2 minus concentration as well. So what we're looking for is this concentration of sort of our intermediate and the silver's concentration. You can attack either one, but just to show you here, if we go back to our, actually down here, so let's come here. If we come back to our individual equilibriums in our stepwise fashion, if we look at the second equilibrium, based off of the first table, we have this number, and we also have this number off of the first table. That would allow us to now directly calculate this guy, since that is one of the things that we are looking to solve for. And that's what I'm going to do here. I'm actually going to use just the second step because I already have 2 of the 3 pieces of information I need to get to the third piece there. And that means looking at step number 2 here, I have a K2 that is equal to the concentration of our product divided by our reactants, which in this case is this, and our S2O3 2 minus here. And again, that's going to equal, as we see there, 3.9 to the 4th. And again, I'm choosing the second one because I already have both of those informations. So if I rearrange here, these 2 guys are going to switch places, and that would give me that this guy's concentration is equal to, I can put my numbers in, 4.29 times 10 to the minus 4. That is this guy's concentration, divided by my K value that I brought over, 3.9 times 10 to the 4. And this guy's concentration here from our table, 2.86. I do not need to square that 2.86 because I am not using this equation. I am using this equation where it is a coefficient of 1. So again, here I'm not using the overall equation for this step, just the second step. And that is why I don't need to square it. Yeah. If I did use the overall equation, I would need to square that number. So we got 4.29 to the minus 4 divided by 3.9 to the 4th divided by 2.86. And that's going to get me a concentration of this guy of about 3.8 times 10 to the minus 9 molar. Any questions on that there? So that now gives me another answer I was looking for, which is what is the concentration of that guy right there. That leaves me one thing that I have left to solve for, which is the silver concentration. And since I used the second one last time, I could now use, if I wanted to, the first equilibrium, because now I have this guy's information from the calculation we just did. I have this guy's information that will allow me actually to get to the silver here by using the first one. So if I did that, I'm going to use K1 down there, which again would be our product, which is sort of that intermediate guy, divided by the silver concentration and the S2O3 2 minus. Once again here, I do not need to square it because I am using this equation, not the overall equation. So that's going to equal 7.4 times 10 to the 8. Putting in our rearranging, since I'm solving for silver, we're going to switch places. And that's going to give me that the silver will equal what we just solved for, 3.8 times 10 to the minus 9, which is this guy, divided by the K value, 7.4 times 10 to the 8, and our 2.86, which is our S2O3 2 minus. Putting in those numbers there gets me 3.8 to the minus 9 divided by 7.4 to the 8 divided by 2.86 gets me a 1.8 times 10 to the minus 18 molar for my silver ion concentration. Once again, my silver ion concentration should be a large number or small number. Small, right? So this again validates our assumption that all of it's going to get used up. We have barely nothing left at 1.8 times 10 to the minus 18 molar. First off, any questions on that? So this demonstrates, yeah. Yeah, absolutely. That's where I was going to go next, actually. So this demonstrates that if you have it in a stepwise fashion, because you did get equilibrium concentrations from the first table, you could go back into each of the individual steps because they're all equilibrium concentrations and you could put it into each step. As the question was just asked, you absolutely could have, if you wanted to, attack silver like we did kind of on the first one first, using the overall equation. And if we did that, just to show you, right, we had a K value of 2.9 to the 13. So 2.9 times 10 to the 13 was our Kf for the overall reaction. And if we write our equilibrium expression for this guy, that would be our product divided by our reactants. And this guy would need to be squared there. I think I put that's a 3 and a 2. This guy here would need to be squared because now we're using the overall reaction. And the overall reaction, we do have a coefficient of 2. So we do need to make sure we do square this guy. And that would equal our 2.9 times 10 to the 13. Just like previously, these two guys would swap places. And if we put in our values from our overall table here into that, 4.29 times 10 to the an old minus 4, that is it, divided by our Kf and our 2.86 that we do need to square in this case. That's going to give us a silver concentration that would be equal to, ideally, should be the same number we just got on the previous slide, but just to verify, let's make sure. Looks like a 1.8 times 10 to the minus 18 molar. So you can see, again, it is the same thing that we got here. At that point, you would need to obviously go back into probably the first one so that you could get to this guy's concentration. Or you could go back into the second one like we did originally as well. So you would have a couple of options to sort of get that last guy's concentration. So you absolutely could use overall reaction, the K value, or you could use each individual steps as well. They all should kind of give you the same one. As long as you are starting with, you do have to do this table first to get to the equilibrium concentrations before you kind of go in there. Other questions on that there? Okay, one last one here to look at, which is a little combo action here. Here we want to calculate the molar solubility of silver chloride in 1 molar ammonia solution. So if we take a look at this, and we have a couple of stepwise things happening here. We have a KSP of our silver chloride breaking apart into silver ion and chloride. And we have a complex ion formed here where the silver ion and the ammonia come together to make this complex ion. So we could add these guys together. And actually, in this case, our silver ion is actually the one that's going to be canceled out in this case, as they are on opposite sides of the arrow. That's going to leave us an overall reaction of silver chloride plus our ammonia going to make our complex ion here and our chloride. And we can't get a K value here. And does it matter if it's KSP and KF? Can we multiply them together? We can, because they're all equilibrium constants. So it's no different than when we did Ka times Kb, right, equals Kw. So same idea. They're all equilibrium constants. So we can get a K value here by, in this case, taking our KSP and timesing it by our KF, since they are both equilibrium constant values. And we'll go 1.6 to the minus 10 times 1.5, looks like to the 7 there. That's going to give us a 2.4 times 10 to the minus 3 in this case. Now, this problem is a little bit different than the other two we did. We are not looking for the silver concentration because it's gone at this point overall. We're actually looking for the molar solubility. So molar solubility should make you think more KSP problem than KF problem, right? So even though we got like a KF in there, we're going to actually do this as a KSP type problem since we are looking for our molar solubility. So we'll take our overall reaction there and just pop it together here one more time. Our silver chloride plus our couple of ammonias, giving us this guy here. And our chloride as those guys go away. And our K in this case would be our silver complex ion times our chloride, as obviously this is aqueous, and solid, yeah, divided by our NH3 squared, right? And that equals what we just calculated there, 2.4 to the minus 3. All right, so we're going to do our ice table like we do a KSP table. This is a little bit different because not only on the left-hand side do we have a solid, but we also have something that should be included, obviously, in the equilibrium expression. We have the ammonia. And we do know the concentration of ammonia is 1 molar here. So we do have that concentration. So we are going to, unusual for KSP, actually have something over there on the left-hand side. This is going to be 0 and 0. And then we're going to go with our change, which will be plus 2s here again. Not plus, I'm sorry, minus 2s. Come here. It's on the left-hand side, so it should be decreasing. So it is minus 2s here. Again, the 2 for the coefficient. This would be plus s and plus s. This then at equilibrium is going to give us 1.0 minus 2s. This is going to give us s and s. So similar to a KSP table, but again, since we're kind of mixing a couple of things together, we actually do have something we need to include there on the left-hand side, which is the ammonia. Any questions on that there? So like normal, we're going to solve this by putting this into our expression. So we're going to go and pop that in there. And that is going to get us S times S divided by 1.0 minus 2s squared is equal to 2.4 times 10 to the minus 3. Now, hopefully you can see this is a little perfect square on both sides. Yeah, so we got an S on top, a 1.0 minus 2s equals, probably don't want to forget square root that guy there, 2.4 to the minus 3. Gonna get us 4 point, I don't know, I'll call it 90 times 10 to the minus 2. We're gonna multiply this to the other side. That will give us S is equal to 4.90 times 10 to the minus 2 minus 9.80 times 10 to the minus 2s. Obviously, here we're going to combine our s's, so we're going to bring that over to the other side, and that will basically get us plus 1, right? So we'll end up with, we'll call it 1.09798s is equal to 4.90 times 10 to the minus 2. Dividing that now to the other side. Obviously, adding that to the other side. Will give us an S here of 4.9 to the minus 2 divided by that. Will give us a S of 4.46 times 10 to the minus 2. That is the molar solubility of our silver chloride. Again, if we turn that into grams per liter, 107.9 for the silver plus 35.45. We will times that by 143.35 grams per liter per mole. Gives us grams per liter. Times our number there. There we go. There it is. Gives us about 6.40 grams per liter can be dissolved in this reaction here. First off, any questions on the reaction are the molar solubility, which is obviously here. Now, for reference sake, if you remember, we calculated earlier that if you take your silver chloride, that has a KSP in water of 1.6 times 10 to the minus 10, and we run through our table like we did in that problem, change plus S plus S. KSP here being our silver concentration times our chloride concentration, 1.6 times 10 to the minus 10. Popping that in there gets you S squared is equal to 1.6 times 10 to the minus 10. Square rooting both sides like we did on that earlier example gives us a molar solubility of silver chloride in water of like 1.3 times 10 to the minus 5 moles per liter. Timesing that by our 143 something, right? 143.35. 143.35 grams per mole. That gave us our 0.002 grams per liter is our solubility of silver chloride in water. Which one is it more soluble in? It is definitely way more soluble in the complex ion, right? And the presence of that complex ion. And that is actually what happens, as I was talking about earlier, when you do those qualitative analysis, you actually, the way you identify whether or not you have silver present is you get your silver chloride solid, you add ammonia to it. When you do, it does this, and it actually goes from solid into that complex ion and rips out the solid and makes a complex ion that's aqueous. And then you add a little bit of acid to it, and it reacts back with the chloride and makes the solid come back, and you can actually tell it that way. But here you can definitely see just by the numbers that when it is possible to form a complex ion and there is a good ligand and a metal involved, that is definitely going to be favored over anything else. It is so favored, as I mentioned here, literally you could make a solid disappear by just adding that complex ion. Is able to remove the silver from the solid and form that complex ion because it's much more favored. Way, way more can get dissolved. Any questions on that there? All right. Happy news is there is some KF values from your book that you might have to look up. And as we've been talking about, you can see they're fairly large to the 43, 35. And again, this should always favor sort of complex ion formation in most cases, if that is possible. That does wrap up chapter 15.